Okay, so here we talk about the force between two parallel currents. So yeah, so it has parallel wires carrying current in the same direction attract each other. So parallel and yeah and yeah for parallel current carrying wire in the opposite direction will repel each other. So something like same side repel each other and then opposite side attract each other, something like that. But here we have the same direction for the current attract each other. Okay, so here so it says the magnitude of the force on a length L of either wire is this expression mu 0 L is the length of the wire, and then IA IB 2 pi d. Okay. Yeah, so yeah. Okay, so D is the separation. You can see here, D is the separation. So it is here, and then L is the force on a length. So maybe we consider only this part. Yes, force on this segment, and then IAIB. Okay, so for this case, you can simply imagine for this. For example, let's consider this wire first. So for this wire, if the IA is going in from slightly left to the right, like this. So this is the IA. In this case, using the Amphius law, we know that the magnetic field generated at this point will be pointing downward, BA, and then actually BA is nothing but mu 0 IA over 2 pi d. We do not use R here, we use a d for the separation of these two parallel wires. Okay, so this is BA, and then from the last chapter, at the last part of the last chapter, we know that the force acting on the current carrying wire from the external field, external B field, is ILB, or if you remember, it is actually FB equals I times L cross B, something like that. But now we consider L and B are perpendicular to each other, so we don't have a sine of theta here, or we have sine of 90 degree here, so it is nothing but IB times L times BA. Because L is pointing to this way and then BA pointing downwards, so these two are perpendicular to each other. And then we can see that the direction of the force is L cross B. So L points to this side, B points to this side, so L cross B points to the the left side, which is towards the wire A. So this is FBA, which is the F acting on the wire B due to the wire A. And actually, here in this case, IAIB points to the same direction. If I suppose, you can also consider that here we consider the magnetic field generated by wire B, and then for maybe this point, BB is pointing upward, and then L is pointing to this side. So L cross B will be something like L cross B will be points to the wire B. So follow the same ways. So we will have FAB here points to the wire B. Okay, so we can just plug this one into here. So we will get mu 0 IAIB and then times L. in the numerator. And then for the denominator, we have 2 pi d. So the expression look like this. Okay, so if you maybe just make IB point to the opposite direction, for example, if we have IB point to the other way around, then now we have L point to the opposite direction. So L cross B point to the opposite side. So in this case, if we have a current going in opposite direction for the parallel wires, then they will repel each other. Okay, so here it says the general procedure for finding the force on the current wire is that you have to find the force on the current wire due to the second current of the wire, and then blah 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 blah. So similarly, if the two current are, so this is the way for the parallel current. Parallel current in the same direction, and then this is the case for the parallel current with opposite direction. So it try to call it anti-parallel. Anti-parallel. Anti means opposite. So anti-parallel means the parallel current with opposite direction current. So we could show that the two wires repel each other, just like what I shown quickly. Okay, so parallel current attract each other and anti-parallel current repel each other. So this is the final conclusion for this part. So far, any questions? Okay. So here we talk about the the most important part in this chapter, which is called the Amphius Law. Of course, it is one of the Maxwell equation, as I just mentioned at the beginning of this chapter. Okay, so here the Amphius Law is written like this. So on the left side, this is so-called a line integral. Line integral. Line integral. 线积分 line integral. And then on the right side, we can see mu0 and I enclosed. So you can quickly compare with maybe you can just no, you cannot. Maybe you should compare with Faraday's law in the next chapter. So here we have a line integral on the left side, and then this is a constant. So we use this similar to how we use the Gauss law, but here is a line integral. The line integrals means for example here, suppose we have a current, 3 current, I1, I2, I3. I1, I3 are pointing out of the page, I2 are pointing into the page. So of course they will generate some B field inside this region. And then we need to define so-called Amphius Law, just like what we define Gaussian surface for the Gauss law. So for Amphius Law, we have something so-called the Amperean loop, or actually a closed loop. Okay, closed loop, which means that this is a closed curve, which means that it starts and then go back to the original point, which form a closed loop. Okay, so suppose we have an Amperean loop. Then for every point on this loop, we can calculate B dot ds. So this is the inner product. For example, for this point, we have B pointing to this direction, and then ds is of course the tangent line at this point. And then of course when we define a closed loop, it has a direction. So you can arbitrary, maybe you can define the loop going this way or the other way around. It is fine, but so later we will determine the sign for this loop according to the right hand rule. Okay, so far we define the loop in this direction. So in this case, at this point ds is the tangent line, and then follow this direction, ds. So we can calculate b dot ds at this point, and then of course we can calculate all the b dot ds for every point, and then we add them together using the Riemann sum. So it is an integration, and then we'll call it line integration. And similar to the Gauss law, the Gauss law have the surface integration for the closed surface or the Gaussian surface. Here we have a line integral for the closed contour or the closed curvature line, curved line. So we draw a circle here to demonstrate it is a closed line integral. Okay, so now we know, actually we can really do the line integral for the left side, and then for the right side, mu0 is the permeability constant. So we just we have already introduced it. So this is I enclosed, similar to the Gauss law, the Q enclosed. So how to find the I enclosed is that, suppose on this surface we have this loop, which is somehow like counterclockwise. So to determine the sign of the current is that you use your forefinger. Follow the direction of this loop. Four fingers follow this loop. So in this way, somehow like this, and then your thumb will pointing out of the page. So out of the page will, which means that the positive current, positive I. If the current is pointing out of the page, we will count it in a positive way. If the current is pointing into the page, we will count it negatively. So for this case, the enclosed current for this loop is I1 minus I2 for this case. I1 minus I2 for this loop. I3 is out of the loop, so we don't count it as the enclosed current. We don't count this one. We only count I1 and I2 because this loop encloses I1 and I2. When I1 is going out of the page, and using the right-hand rule, we know this one is positive, and this one going into the page, which is negative. So we have I1 minus I2 for this case. Okay? So here it says the line integral in this equation is evaluated around a closed loop called an Ampere loop. The current I on the right side is the net current encircled by the loop. And then we can use the right-hand rule. You can use the right-hand rule to determine the sign of the current. So this is out of the page. So this is positive, this is negative. And actually, we will assume that this current is infinitely long from negative infinity to infinity, or the other way around. Okay, so here we will try to use the Amphius Law to show what we got in the last hour, and also we will get another result which cannot be which is another one. So now here we assume this is a wire, but this wire is not thin. Last time we considered the wire is very thin. No, the radius is 0 for the wire, but here the radius for this wire is capital R. This is capital R. Okay, so now we consider if the current is going out of the page, and then it is distributed uniformly. We try to consider the magnetic field or the B field generated by this wire outside and also inside the wire. So for the outside part, it looks so familiar because it is actually like the thin wire generate the magnetic field. because for thin wire, all the point are outside the wire, so it will look like that. So actually, we can just simply use the Amphius law to get this proof. So which is like, suppose we consider the point here, the radius from the center of this wire to here is small r, and then we define the Ampere loop like this. So we have for the first part, we make use of the Ampere's law. Integration of B dot ds equals mu naught I. I is the total current. Because the whole current is enclosed by this Ampere loop. So we have I here for the I enclosed. Okay, so for this one, this Ampere loop is a circle. With a center at this point. So we will suppose all the B field is parallel to ds, which means that B dot ds is nothing but a BDS. Cosine of 0 degree is 1. Okay, so in this case, we also consider the distance from the point of the Ampere loop to the center is a constant. So B is a constant. So it makes it like B times the integration of ds. So the line integration of ds is nothing but the circumference of this circle, which is nothing but 2 pi r. And then, so it will be equal to mu 0 I. So it turns out to be B equals mu 0 I over 2 pi r. So which is actually the same expression as we get from the Amphius law. And then for the second one, now we consider this is the wire. This is capital R. We consider the Ampere loop. This is the Ampere loop, which has a smaller radius than the capital R. This is the Ampere loop. Like this. Okay, so now we consider the Ampere's law, B dot ds, and then equals mu 0 I enclosed. So now we should consider the I enclosed carefully, because some of the I are out of this loop, so we don't consider those parts. And then on the left side, which should be actually the same as the previous case, so it becomes B times 2 pi r. So I do not repeat it again. And then for here, mu 0, and then I enclosed, we will consider the current density is uniform. We consider the current density inside the wire is uniform. So we should have let's see, I over pi capital R square, which is the cross-section area. So it is the current density for the whole wire should be I enclosed over pi small r square. So this is the current density for the inside part. This is the current density for the whole one, and then we assume the current density is uniform. So these two should be the same. So here we should have I enclosed should be I times small r square over capital R square. So we have a I times small r square over capital R square. Pi and pi will be cancel each other. Okay, so here this r and this r square can be partly cancelled. So we cancel this one with this one. So finally we will get B equals mu 0 I, and then we have r here, and then over this 2 pi over r squared. So this is actually the same as this one. This is actually the same as this one. And yeah, so this one is proportional to the r. So I think I should use a small r here rather than capital R, because it stands for the distance from the center to the point we concern. So I should use small r here. So when we consider the B field outside the wire, this B is proportional to 1 over R, inverse proportional to R. And for this one, B is proportional to R, because R squared is R squared is a constant, so it is proportional to R when we consider the region inside the wire. Okay, so actually, you don't necessarily need to remember, because if you're familiar with the Ampere's law, you can quickly derive this expression. Yeah. And actually, this case is somehow similar to the one in the E field when we consider a sphere. When we consider a sphere with some charge inside distributed uniformly, and then we consider the E field outside and then the E field inside the sphere, which is quite similar. For that one, we use the Gauss law to derive the expression outside and inside the charged sphere, and then here we use the Amphius law to find the B field generated by the wire with a uniform charge current density inside and outside the wire. Okay, so here is a sample problem. So here it says the cross section of a long conducting cylinder in radius with inner radius A, outer radius B. The cylinder carries a current out of the page. So the current is out of the page. Current. Okay. So yeah, and the magnitude of the current density J equals this one, which is not uniform, C times R squared. Okay, so C is this number, and then what is the magnitude B at a point that is 3 centimeters from the central axis? 3 centimeters, which is actually inside this wire here. Okay, so yeah, so first of all, we need to consider the I enclosed. So because we need to consider the B field, which is 3 centimeters to the center, so we define the Ampere's loop like this. Okay, so interestingly, it defined the direction of this Ampere's loop to be clockwise. So which is the other way around, which is opposite to this one, So we should consider this I to be a negative current, because just mentioned we use the right-hand rule to determine the polarity of the current, because here this loop is clockwise. So using the right-hand rule, we use a forefinger follow this direction, and then your thumb will pointing into the page. So when we consider the current going into the page is a positive I. But here this I is going out of the page, so it is negative. So if you don't believe, you can try to repeat the whole procedure when you define the Ampere's loop to be counterclockwise, and then you just go through it again, then you get the same expression. So don't worry about which direction you should define the Ampere's loop. Both of them will give you the same answer if you're careful enough, you don't make mistake to the polarity. Okay, so here we try to calculate the I enclosed in this region. Okay, so yeah, so it is actually integration of a j dot dA. Actually, j is pointing out of the page, so j is pointing out of the page also. and then DA is pointing into the page. DA, you should follow this direction. So in this case, we should have a negative sign in the front, and then we have J to be CR square. So CR square, and then this DA in the polar coordinate will be dA equals r d theta. So we have a r dr here, and then integration of the d theta from 0 to 2 pi, which is actually the same actually the whole circle, and then we integrate from actually from a to small r, or maybe you should make it a primes to distinguish this r and this r. Okay, like this. Okay, so this r is 3 centimeter, this is 2 centimeter. We don't really integrate from 0 because this is a hollow wire. We don't have any current inside. Okay, so we can quickly finish this one. So this is altogether r prime cube. So the integration will be r to the 4th power over 4. So this one will become negative c times r to the 4th power minus a to the 4th power all over 4 for this term. And then for this one, it is nothing but 2 pi. So we will have negative pi over 2, and then c times r to the 4th power minus a to the 4th power. So now we can use the Amphius Law. Integration of a b dot ds equals mu 0 I enclosed. So similarly, we have a b times 2 pi r, and then we have a mu 0 times a negative pi over 2 c, and then times r to the 4th power minus a to the 4th power, like this. So finally, we can just move this term over, and actually we can cancel pi and pi here. So finally we will get b to be mu 0, actually we have a negative sign in the front, negative mu 0 over 4 pi, and then here we have sorry, we don't have pi here because pi is already cancelled. We have r here, and then times c, and then r to the 4th power minus a to the 4th power, like this. Like this. So we can plug in the values. So mu 0 is 4 pi times 10 to minus 7. So the 4 will be cancelled with this one. So we have a pi times 10 to minus 7, and then times c is this value. 3 times 10 to the 6th power, and then over r is 3 centimeter. So we have a 0.03. And then here we have a 0.03 to the 4th power minus 0.02 to the 4th power. So this term will be negative 20 mu Tesla. 20 mu Tesla. So here we get a negative value. And as much as we define the Amphius loop in this direction, and with this negative value, which means that the B field is actually should be the other way around, should be counterclockwise. counterclockwise. So this is the direction of the B field generated by this structure. So if you just as I mentioned, if you don't believe, if you feel confused whether I should define the Ampere loop clockwise or counterclockwise, if you define the Ampere loop in the counterclockwise way, so the positive side will be pointing out of the page, which is actually the same as this one. So we will have a positive sign here. So the final answer will also be positive sign, and in this case we still get the B field to be counterclockwise. Okay, I just squeeze it in this page. So up till now, any questions? Okay. Okay, so next we'll talk about the solenoid. So yeah, actually, which is like an inductor, right? An inductor. Actually, we will talk more about the inductor in the next chapter. But yeah, actually, it's just like this solenoid. So you can just wind this wire like this, and then yeah, this structure will generate some B field. So here it says the solenoid magnetic field is the vector sum of the field produced by the individual turns, windings that makes up the solenoid. So for points very close to a turn. So you can see here actually the magnetic field lines generated by this structure is, yes, a bit messy, but we don't necessarily consider all of those, because it says, for example, if we consider the point near here, so the fields tends to cancel between adjacent turns, because here we okay, let me, yeah. So here, suppose this is a solenoid, then yeah, the current will be like, this is going into the page, this is going out of the page. So this is going out of the page, and then going into the page, and then somewhere going here, and then going out of the page. So it is like a loop going from here to here, and then going to here, to here, to here, to here, so on and so forth. So here we consider, for example, for this part, if you consider only this small region, the magnetic field generated by this part will be like this. Just follow the right hand rule. If you use a thumb, follow the direction of the current, and then your forefinger will somehow rotating like clockwise. And then similarly for this part, the magnetic field also rotate clockwise. So right in the middle of these two wire, then the magnetic field from the left wire is pointing downward. The magnetic from the Y wire is pointing upward. So right in the middle, the B field is more or less cancel each other. So you can see the magnetic field lines is quite dense near this region. Okay, so actually we don't really care about this point. And also for the outside part, you can also see the magnetic field outside is also very weak. It's also very weak. Actually, when we use the solenoid, the main part we use is the middle part. It's the middle part. So it says the magnetic field in the middle part of the solenoid will be considered as uniform, and then it will just follow the right hand rule. Just follow the right hand rule. You use your forefinger, follow the direction of the current. Yeah, you can simply imagine this is going out of the page. This is going into the page. So the current is somehow like this, and then the B field will be pointing to the right side. So you just use your forefinger in this direction, and then your thumb will be pointing to the right side, which is the direction of the B field. Okay, so at this point inside the solenoid and reasonably far from the wire, because this part is still close to the wire, but you consider the part which is inside the solenoid and also far away from the wire, which is actually the middle part. So B is approximately parallel to the central of the solenoid axis, which means in this case it is pointed to the right side for this figure. Okay, so then we will try to derive the B field generated by this structure. Okay, so this one is actually the cross section of the solenoid. So this is the whole one, but if we draw it like this, you can hardly see see what we need to indicate. So you can just consider we try to cut it by half. So these are the currents. So this is going into the page, this is going out of the page. So this is going out of the page, going to this one, and then going into the page, and then blah blah blah, going to the second one, going out of the page, and then going to here, going into the page, going to the third one, so on and so forth, like this. Okay, so now we try to calculate the B field generated inside the solenoid with some assumption. The assumptions are not necessarily correct, but without this assumption, then it makes things to be hard to calculate. So we really need some assumption to simplify the calculation. So so the assumption we make here is that the first one, 0 outside it. We don't have any B field outside the solenoid. This is the first assumption. And then the second assumption is that B is totally uniform inside the solenoid. Because in the previous page we mentioned that if it is inside the solenoid, but if it is close to this region, it is not necessarily like this, but we make some approximation. We try to consider all the points inside the solenoid to be uniform, like this. And then outside the solenoid, we don't have any B field. If we make these two assumptions, then it is okay to come up with a very elegant expression. Of course, it is not accurate enough if you really consider the experiment. But at least it is good enough to make a approximation. Okay, so now here we try to consider the Ampere's loop like this. The Ampere's loop like this, A, B, C, D, in this direction. Okay, so here we consider the Ampere's law, B dot ds on the left side, and then mu 0 I enclosed on the right side. So let's consider the line integral first. the line integral is for this rectangle, so we can separate into 4 parts because there are 4 sides for the rectangle. So from A to B, B to C, C to D, D to A. So we have A to B, B to C, C to D, and then D to A. Separate into 4 parts. And after we make this assumption, then only the line integral from A to B has a non-zero value, because we consider B is uniform here. So from A to B, ds is point to the right side for segment AB. For segment AB, ds point to the right side, and the B field also point to the right side. So B and ds for segment AB points to the same direction, which means B dot ds is nothing but B times ds, and B is uniform, so we can just plug it out, which means that this integral of ds is nothing but the length of this AB segment. The AB segment we consider is h, we denote it as h. So this line integral is simply written as b times h for this segment. And for the other segment, all of them are 0, because for BC, this B field is pointing to the right side, this is pointing upward, and this ds is pointing upward. So they are perpendicular to each other. So B dot ds is 0. And for the outside part is of course 0. And so similarly, dA, the line integration of BDS for dA segment is also 0. And for CD, it is totally out of the solenoid. We assume B is 0 outside the solenoid, so this part also contributes 0. 0 here. So all these 3 terms are 0, and then this is BH. So this whole line integral on the left side is BH. So we have a BH on the left side, and then for the right side, we have mu 0, and then I enclosed. We really need to count it a bit. Yeah, so this is counterclockwise. So using the right-hand rule, the positive side is pointing out of the page. We just show 4 finger follow the direction of this Amphius loop, and then your thumb is pointing out of the page. So pointing out of the page is a positive current. So in this case, we need to count how many numbers of a current are going out of the page within this Amphius loop. So actually, the total current enclosed will be actually the current of this solenoid multiplied by the number of turns in each in here. So it is like I times the total number. This is the total number of turn. In this segment. Okay, so we can try to slightly rearrange the term. We will have B equals mu 0 I n over h. So n over h we will denote it as small n, which is small n is the number of turn per unit length, because this capital N we will consider is the total number of turn for this segment, and then we divide it by h. So this is actually the number of turn per unit length. And in this 1 or 2 chapters, we will generally use capital N to stand for the total number of turns, and then small n for the number of turns per unit length. Okay. So we should be careful. You should be careful about the whether the n is capital or not. So we have mu 0 in here, mu 0 in here. So with these two assumptions, we got an elegant expression for the B field inside the solenoid. So this expression is this one mu 0 is a constant, of course, and then I is the current, and then I is the total number of turns. So if the total number of turns, the number of turns per unit length, if this number is larger, we can generate a larger magnetic field. So which is so trivial, because every turn will generate the B field in the same direction, so they will add up. So it makes the total B field at that region to be stronger. Okay, so so here we also consider the magnetic field of a toroid. Magnetic field of a toroid. So a toroid is somehow like a solenoid when you try to connect both ends together. So a toroid may be described as a hollow solenoid that has been curved until its two ends meet each other, forming a sort of hollow ballast, 像个手链那样. Okay, so you try to, so suppose this one is much longer, and then you try to connect this part to here, so it becomes the shape like this, like this. Okay. So here we also try to find the B field generated by this structure. Okay, so here we consider the current is going into the page for this loop, and the current is going out of the page for this loop. Here we try to of course we still use the same approximation that the B field is 0 outside this toroid. It's 0 outside the toroid, but here we don't have uniform B field inside the toroid, and of course we can just define the Ampere's loop with the orange Ampere's loop, and I think the Ampere's loop is clockwise. It's clockwise. So so here we use the Ampere's law. Mu I enclose. Okay, so on the left side it is nothing but B times 2 pi r, and on the right side mu 0 I enclose. I enclose is the I, is the single I multiplied by the total number of turn here, because it includes all the current. So this n is capital. And then when we consider the sign, here we have the Ampere's loop to be clockwise. So using the right hand rule, we know that the positive direction is going into the page. So here all the current are going into the page. So so this is positive. And then we move these terms over, so we get B equals mu 0 I n over 2 pi r, like this. So inside the toroid, the magnetic field is related to the distance from the point here to the center. Related to r, which is not constant inside the toroid. So B is not constant over the cross section of the toroid. Okay. Maybe I think we can quickly finish this one before we finish today. Okay. So it says a solenoid has length L and then inner diameter. It carries a current I. So it consists of 5 closed pairs of layers, each with 850 turns along the length L. What is the B at this center? So we consider a solenoid here, and of course we should use B equals mu 0 I n. So mu 0 is nothing but 4 pi times 10 to minus 7, and then I is this one, which is 5.57, and then times small n we should consider we totally have 4 packs, so 5 packs, I mean 5 packs, so we have 5 multiplied by 850 turn along the total length, so we need to divide it by the total length, which is 1.23 meter, 1.23 meter, because it is around the length L, so we need to divide it by L to find the unit length. But here we have totally 5 closed packs, so we multiply by 5, so this number is 2.42 times 10 to the negative 2 Tesla. Okay, so I think I can just stop here today. February 24, and